So today we're going to learn about the common ion effect. In a saturated solution of lead chromate, an equilibrium is established between the solid and its ions in solution. So let's write what that looks like. So we have lead to chromate. Lead has a charge of 2, chromate also has a charge of -2. Pb is positive 2. So that's solid. We've said it's in equilibrium in solution. So we have Pb ions plus CrO4 ions. Oops. Okay. If you look up in your data table, you can find the KSP value for lead chromate. It's 2.3 times 10 to the negative 13. And this one actually had an error potentially on the one that I printed for you. It might be under the chromate section, but it doesn't say chromate. There's one solid that has 2 values. You just need to look at the table. There is a typo. Okay? And this is going to equal to the concentration of lead ions times the concentration of CrO4 ions. That's just the equilibrium constant. We put the 2 aqueuses, the concentrations, multiply together, and that gives us 2.3 times 10 to the negative 13. Okay, but what if we added PbNO3 lead to nitrate solution? Okay, so what if we were to add to this PbNO3 a solution of that in equilibrium? So we would again have lead 2 ions. Notice we have them here and here. And we would have NO3 ions. Okay, so all of a sudden, we have more Pb2 plus ions in solution. And Le Chatelier is going to tell us something. So all of a sudden, we've taken this side of the equation and we've increased the concentration. We've added a new solution that has even more lead 2 in it. So if we increase the concentration on this side, Le Chatelier says we're going to shift left and we're going to increase this side. In other words, we're going to have more solid. And that's what it says here. And Le Chatelier says we're going to shift left, we're going to have more solid in response to the increased concentration of lead 2 ions. The Pb2 is the common ion. It lowers the solubility. It lowers the solubility because all of a sudden now we have more solid, less solution, and makes something called a precipitate. That is just a solid in solution. Okay? So a common ion lowers the solubility of an ionic compound. Okay? That's the whole idea here. Is when we add something that's already in solution, it's actually going to lower the solubility. Okay. Now how we can predict the precipitate. You can use those KSP values, so you have a data table in your booklet, to predict if a precipitate will form when 2 solutions are mixed. A precipitate will form if the product of two ions, oops, I forgot a word. If the product of the concentration, so you're going to add that, concentrations of 2 ions in the mixture is greater than the KSP of the compound formed from the ions. Okay? So we're looking for the product to be greater than the KSP. So here's an example that we're going to do. Suppose we mix half a liter of 0.08 moles per liter of sodium sulfate with half a liter of 0.002 moles per liter of barium nitrate. my question is, will a precipitate form? Well, first of all, let's look at these solutions. Solution, I probably should have written, just to be correct. So maybe add solution to your notes. Okay, let's look at each of these solutions. So I have Na2SO4 solid, and it's going to go in solution to, we're going to have sodium, and we're going to have SO4. Okay, is this balanced? Well, no, it's not. There's 2 sodiums on the left side, so I'm going to need 2 sodiums on the right side. I'm purposely leaving some space here, so you're going to want to do that as well. Here I have barium in solution, and that's going to go to Ba2 plus 2NO3 negative 1. So I already balanced that one. Those are in solution. 2NO3, 2NO3s. Good. Okay. Now, what is going to happen? Possible precipitates. We're either going to have barium SO4 or sodium with NO3. So those are my possibilities. So we're either going to have NaNO3. Sodium has a charge of 1, NO3 has a charge of negative 1. Or we're going to have barium SO4. I'm just going to press pause for a second and bring up the data table so we can see if they form precipitates. Okay, so I think I just found your data booklet, and we're going to look at this table. Hopefully you've seen this before. This table right here is what we're going to look at. Let's see if I can get this so we can see everything we want. So we're looking at NaNO3 or BaSO4. Well, let's look. NaNO3. It says any negative ion with sodium is soluble. So no matter, that's always soluble. It's never going to form a precipitate. Now let's look at barium and SO4. Well, barium isn't, sorry, this is just driving me nuts here. BaSO4. Well, here I have Ba, but that's not SO4. Oh, here's SO4. SO4 plus barium has low solubility. So that's my only possibility that there could be a precipitate. So let's write that down here. So this one we said is soluble. We got that from rule 1 on that table. So spend a second, pause right now and get that table out and make sure you understand how we used it. And BaSO4 was low solubility, and it was rule 8. So really what we're looking at is BaSO4. So let's look at BaSO4. Its KSP, let's see if we can find it. KSP here. Here's our KSP table. We're looking at BaSO4. This was the one I was talking about that had that error, PB phosphate. See, it says CrO4, but the chromates are all over here. So this is just a typo. This should be PO4 with that 2 that comes after here. So just so you know, that's what I was looking at. I was alluding to. Okay, BaSO4 has a KSP value of 1.1 times 10 to the negative 10. Does everyone see that right there? So it has a KSP of 1.1 times 10 to the negative 10. There is no units for KSP. Okay, so what we had said before is that a precipitate will form if the product of the concentrations of the two ions is greater than the KSP? Well, what two ions make up BaSO4? Well, it's going to be my Ba from here and my SO4 from here. So, what is the molar solution? Well, SO4 came from here. It had 0.008 moles per liter when it was half a liter. But now we have 1 full liter. So its concentration, it just got diluted. It just went from 0.08 moles per liter, and now there's twice as much solution, twice as much like water, but there's still just that many moles. So this actually goes in half, 0.004. Okay, another way I think I showed this before is I said, well, we have 0.008 moles per liter times, we only had half a liter of it, so we just, when we times that, we got 0.004 moles, and then we had a total of 1 liter because it was half a liter plus a half a liter, and that gave us our 0.04. Using that same principle, Ba, the concentration of Ba, well, we had 0.002 moles in half a liter. Now we've increased to 1 liter, so we have diluted it by a half. So we have 0.001 moles per liter. So I have said that if the concentration of those two ions of barium, which was 0.004, and 0.001, which is that SO4, sorry, that's the barium, this is the SO4. If that product is greater than 1.1 times 10 to the negative 10, it will form a precipitate. Well, let's look at this. This is 4 times 10 to the minus 6 when you multiply that out. How does this compare? It's greater than KSP. So that means a precipitate will form. Precipitate of BaSO4 will form. What you get to hand in is this next question here. Will a precipitate form with half a liter of 0.02 moles per liter of silver nitrate and half a liter of 0.01 moles per liter of sodium chloride? Your answer, you need to tell me either yes or no if precipitate will form, what precipitate will form if it's yes, and either if it's yes or no, you need to show the calculations to show how you came up with that answer. So it's very similar to the example I just did. Shouldn't be too difficult. Just send me an email or a text if you have questions.